Okay, so we're continuing 4.7 and we're just doing examples. So here's one. A piece of wire of length L is bent into the shape of a rectangle. What dimensions produce the rectangle with the maximum area? Now how should I start? Well, let's start with our piece of wire and draw a little picture. So there's my wire of length L. That's bent into the shape of a rectangle. So the rectangle would be like that. Right, so these are the two ends of the top and the bottom of the rectangle here. And so let's just call the two sides x and two sides y, right? Okay, so now with this picture, what we're trying to do then is we're trying to maximize the area, right? Which is xy. Now if I were to stop there, there is no maximum, right? Because x and y could just grow as long as they want. However, there are some restrictions. For one, x and y have to be greater than or equal to 0. So we might even say restrictions. X is greater than or equal to 0, y is greater than or equal to 0. And the perimeter of the rectangle, right, can't be bigger than L. So therefore, 2x plus 2L, or 2y, is equal to L. Good. And so now we have our function and we have a side constraint. We could solve for one of the variables using the side constraint to get a function of one variable, right? So if I take this, I can say, by the way, can you tell here if there's a maximum value for x and y? Right, x and y could not be any bigger than L over 2. X must be less than or equal to L over 2, and y must be less than or equal to L over 2. Okay, so now let's go ahead and solve. Maybe for y, so we'll take y to be equal to L minus 2x, that's 2y, and then divide by 2, or multiply by 1/2. Okay. Alright, so that's you could write it as L over 2 minus x, I suppose. Alright, so now, going back to the area function, we want to find the max of the area, which is now x times L over 2 minus x, and now x is between 0 and L over 2. The nice thing about that is we have a continuous function over a closed interval. We know exactly how to work that, right? By the way, we're already seeing, right, that the area using 0 is 0, and the area using L over 2 is 0. So whatever critical point we have in between, right, as long as it's positive, that's going to give us a max. So let's go ahead and find our critical points. So the derivative of a with respect to x is going to be L over 2 minus, let's see, that's minus x squared, so that's going to be minus 2x, right? And so if we set that equal to 0, we see that x must be equal to L over 4. What kind of a rectangle is that going to give us? Can you guess? If x and y are each x L over 4, then yeah, it's a square. Good, so the max, the shape that gives the max area is a square with side length L over 4. Good. All right. And so this, let's try one more now. And I want to bring in a little factoid from physics that we should remember from school. It's about how distance, rate, and time go together. And the formula is that distance is equal to rate times time. Right? So for example, if we're going 60 miles an hour for 2 hours, we have gone a distance of 120 miles, right? So, or you could write this as distance equals rate times time. Okay, so this is a formula that is kind of assumed that we know in the next problem. So in the next problem, we're going to be looking at the time that it takes us to get to travel. And so we'll notice that from this formula, we see that time is going to be just divided by r. And so time is equal to the distance divided by the rate. Good. All right. So I'm going to pause for a moment and write down the next question, and then we'll continue from there. All right. So this is a little bit of a wordy problem here. Let's see. Our house is 4 miles from the highway. That's the shortest path. So it's a straight line to the highway. And the distance from that point on the highway to town is 9 miles. We'll assume it's straight. The speed on the dirt path from the house is, or just on the dirt road in general, is 20 miles an hour, and the speed on the highway is 60 miles an hour. How should we build a road from the house to the highway to minimize travel time? So before we start, remember what we did in the last problem. We draw a sketch first and take a look at some of our units and see what we need to do. So in this case, our house, let's see if I can do this both at the same time. So we have a house here, we'll say, and going to the highway is here. And so here's the point on the highway that's closest to the house, and we said that that was 4 miles. And then the town is over here, and this is 9 miles. And so I could build the road, right, to different points on the highway to try to minimize my travel time. And so just to kind of get this more concrete, right, suppose that, so let's call this trial A. In this case, we'll go straight from the house to the highway and then down the highway. And so the time in this case will be, remember that it's going to be distance over rate. And so in this case, we're going to have 4 is our distance. So 4, let's see where I'm going to put this, 4 over 20 plus 9 over 60, right, is going to be miles and miles per hour. And so overall then, that's going to be, let's see, I think I can reduce that. So put it over 20, 4 plus 3, 7 over 20. Okay, and this is in hours. So 7 over 20 hours. Good. Now what's the other, so that's the extreme, right, where we just go straight this way and then straight this way. The other extreme, right, is to just go all the way from the house to the town on the dirt road. So trial B, we're going again all the way on the dirt road, and so I need this distance here. Maybe I'll call it running out of variables. Oh, let's call that h. Okay, so then I can find the value of h, right? So h squared, or h is the square root of 4 squared plus 9 squared. Okay, so that's going to be the square root of 97. And that's about 9.84 miles, okay? But we need the distance, or the time traveled, so that's our distance. Square root of 97 divided by 20 is our total time traveled. Okay, and so that's going to be approximately 0.494 hours. Okay, now what we want is, we don't want to, we may not want one of the extremes, we want to say go this way first and then travel this way for the rest, right? And so let's make this x right here, right? And so this will be 9 minus x then. And so do you see what we're going to be doing here? So the travel, or the distance traveled on the dirt road, is going to be the square root of 4 squared, or x squared plus 16, right? Good. And then this is the distance that we drive on the highway. So the total time traveled now is going to be the square root of x squared plus 16 divided by 20 plus 9 minus x divided by 60, right? Good. Now, let's call this t of x. And remember that x is running from 0 to 9. We've already done the case where we had 0 and 9. And so we're just really looking for the critical point then in between. So let's go ahead and differentiate. T prime of x is equal to, let's see, that's going to be 1 over 40. Oops, gosh darn it. 1 over 40, 2x over the square root of x squared plus 16 minus 1 over 60 equals 0. Okay. Now, let's see, we could simplify that a little bit. Looks like we get 2x over the square root of x squared plus 16 is equal to 2/3, right, by bringing over this and then multiplying both sides by 40. Divide by 2, we get 1/3. Good. And now we get 3. I'm cross multiplying. 3x equals the square root of x squared plus 16. And the best way to solve that is to square both sides, but you got to be careful about that. 9x squared equals x squared plus 16. You have to be careful that you don't introduce spurious solutions. So now we get 8x squared equals 16. Yay! X squared is equal to 2. So x is equal to, well, plus or minus the square root of 2, but we'll just take the positive root since our value is positive. Good. All right. So we could plug the square root of 2 into t of x here using a calculator. And if we do that, we see that t of 2 is approximately 0.3385. And so now compare the three values that we have, 3385 to 0.494 to 7 over 20. By the way, the 7 over 20 is 0.35. And so you see that this value minimizes global minimum. Good. We ran out of time, so I better stop there. But we can see that the best place to build the road will be square root of 2 miles down the road from our shortest point. Good. See you in the next video. We'll just do a couple more examples.